In section 2.1, we are finding patterns and using what is called inductive reasoning. Okay? Inductive reasoning is reasoning based on patterns you observe. Now, what do I mean by reasoning? Thinking, problem solving. Okay? That's what reasoning is. It's thinking or problem solving. So, inductive reasoning is reasoning based on patterns that you observe. You actually have to see these things. Okay? Let's go through and do some more vocab before we start looking at our examples. Yes. Down at the bottom, we have something else called a conjecture. Or in the middle of the page, I guess it is. A conjecture. You may want to find the 10th or 100th term in a sequence. So in this case, rather than finding each individual term in a sequence, we can find a pattern and make a conjecture about that term, which then might help us find that term. So a conjecture is a conclusion you reach using inductive reasoning, looking at a pattern. So for example, think back to Caveman Grog, I'll call him. So Caveman Grog picks up a rock, lets it go, and it falls. Right? Right. Picks up another rock, lets it go, what's it do? Falls. Picks up a third rock, lets it go, what's it do? Falls. Picks up a fourth rock, but then ponders to himself. What's this do? Okay? What if he lets go? Does he have to let it go to know it's going to fall? No. Now, don't say because he understands gravity. He doesn't. He's a caveman. Doesn't understand gravity. But he knows it's going to fall because he saw 3 rocks before that fall. Right? He observed a pattern. He had 3 examples before that if he lets go of this rock, it will fall. So the 4th rock, without even letting it go, he knows it's going to fall. Right? That's inductive reasoning. Okay? And then that was his conjecture as well. He knows that if I let go of this rock, it's going to fall. That's his conjecture. So he could pick up 15 rocks, and each and every one of them will fall when he lets it go. Okay? So there's an example, though a very silly example, of what inductive reasoning is, and then what a conjecture will be. Okay? So let's take a look at a couple examples. So starting out with our first one here, they want us to look for a pattern and then find the next 2 terms. Now, when looking for a pattern, there might be multiple patterns. Okay? Usually, in this class, for the examples I'll be giving you, there's going to be only one set of right answers. Because even if you do a couple different patterns, they still come out to be the same answers. Okay? But just remember that if you find a different pattern than your friend next to you, it doesn't mean you're wrong. Okay? So, looking at this part A, how do we go? We've got to find our pattern. These are our 3 examples, our 3 observations. How did we go from 3 to 9? Okay, I could have said I squared it. I could have said 3 squared gave me 9, but can I continue that logic? Can I say then 9 squared is 27? That one didn't work. Let's see here. How about... Okay, well, hold on. I'm hearing multiple things here. Hold on. So I'm hearing times 3. I can't erase that right now. So times 3 gives me 9. Then times 3 gives me 27, right? 27 times 3, does that give me 81? Yep. Okay, so we can continue that pattern. What's 81 times 3 then? 243. Okay, and what is 243 times 3? Okay, very good. So that would work. There's our next 2 numbers in our sequence, 243 and 729. But I also heard people say, hey, use different exponents, right? Well, what if I had said that 3 was 3 to the 1st power? 9 is 3 squared. 27 is 3 cubed. Because 3 times 3 is 27. 81 is 3 to the 4th power. So then how am I going to find the next 2 in my pattern? 3 to the 5th power, and then 3 to the 6th power. And that's what you meant to say? Okay, beautiful. Beautiful, beautiful. Okay? Questions? Finding a couple patterns. Both patterns give you the exact same answers here. Okay? So make sure when you're looking for patterns that you try lots of different things. Because some of these patterns in your homework are a little tricky. When I show you the answers tomorrow, you're going to go, oh, I didn't even think of that. Okay? So try to look for some different patterns if you're stuck. Okay? All right. Let's try example B. Picture patterns. I like picture patterns. Lets me draw. So we've got to draw the next two pictures in our sequence. So first off, looking at our patterns here, what's the thing staying the same? Circle. So both of our next two patterns have to have circles involved.
It's adding a point every time.
It's adding a side to our polygon, or you could say it's adding a vertex or a point. And point by meaning actually a corner, a pointy point, not a geometrical point. Okay? Yeah, it's adding a side or adding a vertex to our polygon. So our first diagram has three sides, or you could say three vertices, or points at the or corners, I should call them. The second diagram has four sides, or four corners. Third one has how many? 5. So what's the next one going to be? 6. So we can take our best shot at drawing a 6-sided polygon here, which is called a hexagon. That'll work, okay? It's not great, but that'll work. 6-sided polygon. And then what's the next one going to be? 7-sided. Okay, now I'm just going to give you a hint. When they're having you draw polygons inside circles, probably the easier way to do it is to draw the number of corners you have. Because in the triangle we have 3 sides, but we also have 3 corners. In a square we have 4 sides, but we have 4 corners, so on and so forth. So our next one's going to have 7 sides, so it might be easier to try to evenly space 7 corners. Something like that, which mine aren't totally evenly spaced, but you get the idea, and then we can connect the dots. Sometimes just connecting the dots is an easier way to draw your heptagon, is what this is actually called, rather than trying to freehand draw it inside the circle. Okay? All right. So, we have picture patterns. Wonderful. Questions on finding patterns here? I mean, these are relatively straightforward patterns here. Let's take a look at writing conjectures. So, using inductive reasoning, we want to look at the circles and decide what conjecture we can make about the number of regions 20 diameters will form. So, we're starting out with a circle. And in the first diagram, we're drawing 1 diameter. Please remember, a diameter is a segment that is cutting the circle in half, right? It's that longest segment across the circle. And so we're cutting our circle in half with 1 diameter. So if we have 1 diameter, how many regions of the circle is it divided into now? 2. Okay, well, in the next diagram, we have 2 diameters. How many regions do we have? 4. And in our third circle, we have 3 diameters. Oops, I changed colors on you. 3 diameters. How many regions do we have? 6. Do you see any patterns going on here? It's going to be what? Double the number of diameters. Yeah. So let's just say the regions are double the number of diameters. All right, well, let's test our conjecture here. Let's test it. I'm going to draw a circle, and I want to draw 4 diameters. So 1, 2, 3, 4 diameters. And that's cutting this circle into, well, how many do we think it's supposed to cut it into? 8. Let's see if it does. 1, 2, 3, 4, 5, 6, 7, 8 regions. So we know our conjecture works. Okay, we know our conjecture works. So therefore, what do we know about the number of regions with 20 diameters? 40. There's going to be 40 regions. 20 times 2. So I will say with 20 diameters, there will be 40 regions. All right, let's go ahead and try a couple of other examples. Let's take a look up here. I would like you guys to try these 3 patterns on your own. Okay? When I say on your own, if you get stuck, you can discuss it with your neighbor. Okay? But I'm going to give you guys about 2 minutes to try to work these 3 examples on your own. Ready, set, go. Okay, so coming back together here, let's see what we can discover. So in our first example, we have 45, 40, 35, 30. What pattern's going on here? Yeah, we're subtracting 5 each time. So minus 5 there, minus 5 there, minus 5 there. So 30 minus 5 gives us 25. And then 25 minus 5 is 20. So there's our next 2 numbers in our pattern. Great. Looking at the picture pattern. What's staying the same? The outside box. I'm going to call it a box, a rectangle. It's not quite a square, but oh well. So I have this rectangle here. And then for my next diagram, looks like they're taking the midpoint of each side and connecting them to make a diamond shape. Right? Everybody see that? Okay, and then looking at the third diagram, looks like again they're taking the midpoint of each side, connecting them to make another rectangle. So what's on our next diagram going to be? Another like diamond on the inside, right? Yeah, exactly. So it should look like this, or something very similar to this. So there's the second image. Here's the third image. And then here is our new fourth image. I got a little sloppy, but you get the idea. Okay? Well, the next image, because they wanted us to find the next 2 in the sequence, we have our rectangle, the diamond inside that, the rectangle inside that, the diamond inside that, and then another rectangle. Okay? Everybody got those? Everybody got those? All right, cool. All right, so looking at the next image, we have letter patterns. All right, well, we see RWB, then RWB, so I bet RWB is getting repeated each time, right? Yes. Okay, the issue on this one, of course, is how do you find the 21st image, or 21st term? What do you think?
So, like, you got 3 in each pattern, so if you times that by 7, that's 21.
Okay.
Write it out, and you'll have, like, 7 sets of 3, and then the very last one will be your letter.
Hey, I like that a lot. That's exactly how I would have done this. I would have said, well, I have my first set of 3, my second set of 3, and then if I'm trying to get my 21st letter in the sequence, 21 divided by 3 gives me 7. So I'm going to have a third set, a fourth set, a fifth set, a sixth set, and a seventh set of those 3 letters. And in that 7th set is going to be RWB. So what is the 21st letter in the sequence? B. B is then the 21st. Because we have our first number here. R is our first number. There is no 0 number in a pattern. There's only a first number. Okay? So we go from our first number to our 21st number. It will be B.
I just took 3 times 7 because the third number was the third letter was B.
And so then you knew that we were going to the 21st, and B has to be that last one, right?
Yeah, because it's 3 times 7. So
Yep.
3 is the last one.
Yep, absolutely. Perfect. Wonderful. And so, of course, if you were trying to find the 22nd, you would have to go down to a number that's divisible by 3. 21st. And then your next pattern would be RWB, so then the 22nd number would be the R. See how I'd figure out those odd numbered ones that aren't divisible by 3? It'd be a little more difficult, but it can be done. All right, very good. Let's do one more thing about making a conjecture. not always are you going to have to make a conjecture and then try to find a number in the pattern. Okay? Sometimes they just say, find a conjecture. Make a conjecture. Okay? So for us to make our conjecture, we have to actually use inductive reasoning. Now, just to remind you again what inductive reasoning is thinking or problem solving, looking at specific examples, looking for a specific pattern. Okay? That's inductive reasoning. We have to actually look at examples here. So we want to know, what conjecture can you make about the sum, what does sum mean? Adding. The sum of the first 30 even numbers. Now, before we get too far here, we do have to remind ourselves, what the heck is an even number?
What is an even number?
Okay, but what makes it even?
The fact that it's not odd.
It's divisible by 2. That's what makes a number even. It's divisible by 2. Okay?
Wait, what about 0? What's that?
I suppose 0 could be considered an even number, but I usually take 0 out of the mix of things because it's a special number. It's neither positive nor negative, all that kind of good stuff. It's just 0. Okay? But even numbers, you're right. 2, 4, 6, 8, all that kind of good stuff. So let's take a look at some examples. What if I take the first 2 even numbers? So 2 plus 4, what's that give me? 6 if I add them together. And then let's take the next set. So I have 2 plus 4 plus 6 equals 12. Then I have 2 plus 4 plus 6 plus 8 equals 20. Okay, so looking at, there's my first 3 examples. Now, of course, they want us to go for the first 30 even numbers. Right now, we only have the addition of the first 4 even numbers. But what are you seeing happening here? Is there a pattern, or is there something that we're noticing? They're all even. They're all even. Our answers here are all even numbers. Now, I have heard some people saying, well, the first 2 go by 6. It goes up by 6. And I'm like, well, yeah, of course it went up by 6 because I added 6 to it. Right? And well, the next one goes up by 8. Well, yeah, of course it did because I added 8 to it. So that's not really a usable pattern for us, right? That's not really a usable pattern. But the fact that our answers are all even, that might be it. Let's go ahead and see if we test it again. What's 2 plus 4 plus 6 plus 8 plus 10? 30. Is it even? Hey, that is a usable conjecture then. We can say that the sum of the first... Now here's a key thing. I am restating the question, what they wanted me to find a conjecture for. I am restating that. The sum of... Oops. The first 30 even numbers will be even.
Just because it sounds obvious.
Well, some of this stuff is going to seem obvious. Kind of like that very first example. What's the 2 numbers in this next numbers in the sequence? It wasn't a difficult pattern to find out, right? We were just multiplying by 3 each time, or using exponents. 3 to the first, 3 to the second, 3 to the third. It wasn't a terribly difficult pattern. Some of these won't be difficult patterns. Some of them will be pretty basic. But the point being is, even though this might be considered an easy conjecture to come up with, it's still a very true conjecture, and we know it because we used inductive reasoning. We looked at examples to show that, yes, if I add those together, I'm going to get an even number. Okay? And that could have been another conjecture we could add to this. Absolutely. All right, looking at the back side of our notes, we have another definition. It is called a counterexample. A counterexample, because it says not all conjectures turn out to be true. Okay, you can almost think of a conjecture as like a hypothesis in science, right? Just because you make a hypothesis and test it doesn't mean it's true. Okay? So, not all conjectures turn out to be true. So, you should test your conjecture multiple times. You can prove that a conjecture is false by finding one counterexample. Okay, you can prove a conjecture is false by only finding one counterexample. That's all you need to disprove a conjecture. Because by making a conjecture, you're saying that that's true all the time. And so therefore, we only need one counterexample to disprove it. Okay? So, a counterexample is an example that shows that a conjecture is incorrect or false. So, what is a counterexample for each conjecture? They are saying, if the name of the month starts with the letter J, it is a summer month. Well, sure, June is in the summer and July is in the summer. What about January? You can connect any 3 points to form a triangle. What do you think about that? Okay, but that's 2 points, so then what do you also need? Yeah, so 3, what? 3, what's another vocab word for that? 3 collinear points. Yeah, if you have 3 collinear points, you can't draw a triangle. Yeah. So how about 3 collinear points? Because if I have 3 collinear points, the best I can do is draw a line segment through all 3, but I cannot draw a triangle. Okay? When I multiply a number by 2, the product is greater than the original number. For example, now this is not a counterexample. This is an example of what they're trying to say. They are saying, well, if I take 3 times 2, I get 6. And 6 is bigger than 3. Right? That's an example of what they're trying to say. What's a counterexample, Sarah?
0 times 2.
Why not 0 times 2? So let's see. Counterexample, 0 times 2 equals 0, and 0 is not bigger than 0. It's equal to 0. See what I'm saying? So that would not work. I'm hearing some people shouting about negative numbers. What about negative 3 times 2? That gives me negative 6. Negative 6 is less than negative 3. So again, that's another counterexample. We could actually have a whole bunch of counterexamples on this one. Okay? Questions on finding counterexamples. All you're trying to do is find that one example. There might be more than one, but you're trying to find one example where the conjecture is false. Okay? So let's see what you can do here on a couple more. I'm going to give you these 3. And again, I'd like to give you a couple of minutes with your neighbors to see if you can come up with the answers. All right, so trying to come up with counterexamples here. The first one says that if a flower is red, it is a rose. So we're starting out with a red flower, and we're definitely saying it's a rose. What are other flowers? You could have a red daisy. You could have red tulips. You could not have spray paint. You could have poinsettias. Absolutely.
Oh yeah.
Okay. Yeah, there are lots of red flowers out there, and they're not all roses. Okay? And furthermore, it kind of falls apart because just because it's red doesn't mean it's a rose, because there could have been white roses, right? Not all roses are red.
Just because it's a rose doesn't mean it's a flower.
All right, so I'm just going to go with the tulip. All right, let's see here. Part B says one and only one plane exists through any 3 points. Now, here's a couple of things. When you're looking for what this is actually saying, what this conjecture is saying, be careful for the classifiers, okay? They are taught being very specific. One and only one plane. You can't say, well, this one and this one. No, they're talking one and only one. And they're saying through any 3 points.
But you can't have a plane if they're all collinear points.
Right. Collinear points causes a problem. Because if those 3 points are in the same line, you could have infinite number of planes going through those 3 points.
I was going to say if 2 planes intersect, if a plane like stretches out in an infinite manner, then couldn't more than one plane intersect with 3.
Moving on, part C here. When you multiply a number by 3, the product meaning multiplication, the answer to a multiplication problem, the product is divisible by 6. That's a great example. Let's say 3 times 3, that gives me 9, but 9 is not divisible by 6. Okay? So, yeah, 3 times 7. Okay, 21 is not divisible by 6. So all good examples, all right? All good counterexamples, I should say. All good counterexamples.